Population ecology today? Populations are dynamic, highly dynamic. And we often work in ecology in terms of snapshots that we take of systems. We freeze systems in place in order to study them. But those snapshots have to be understood in the context of a roll of film as more like a movie, because these systems never cease in their process. And so all of ecology is a study of dynamics, really. It's a study of processes, some of which stay still long enough that they can be studied statically, in place, frozen in time. We're talking about population dynamics today. We'll start where we left off last time with life history trade-offs, and then talk about life history tables, which are a critical ingredient in demography, in the study of populations, to assess population dynamics. We'll look at population growth models, a couple of population growth models, including the exponential growth model, and look at it in light of laboratory populations and real-world populations. We'll look at population regulation and how populations undergo controls, experience constraints in their growth. And with that, we'll talk about the logistic growth model. These are things you're getting introduced to in lab also. And we'll probably end with a discussion of alley effects at the very end. Remember our all-important principle of allocation, in the light of which we can think of organismal ecology. The necessity of organisms to devote a certain amount of resources to basic maintenance of their physiology, in order to survive. Extra resources can be dedicated to other processes within the life history of the organism. More can be devoted to growth, reproduction, and defense when resources are flush. When conditions are stressful, for example in high heat conditions, more energy, more resources need to be dedicated to basic maintenance, and less is then available for those other processes. And some organisms in a difficult period might shut down the reproductive process completely and fail to breed for a particular season because they've dedicated all of their available energies just to surviving. A few examples of these trade-offs from study populations. Fecundity, I suspect you bumped into that term in the evolution section. It's just an old term for reproductive effort. So growth, in this case the growth of Douglas fir trees, measured in terms of the width of their growth rings, their annual rings. Probably you bumped into that, the fact that you can measure tree growth in the temperate zone, at least, by measuring the width of the growth rings in the trunk of a tree. Well, what these guys were able to do was to look at the width of the growth rings of these trees as an estimator of growth in relation to how many cones were produced on the tree as a measure of fecundity, reproductive effort. And what they found was that the more the tree grew, the fewer cones it produced in a particular year. There was a trade-off between growth and fecundity. Just an example, an empirical example that fits the theoretical model of the principle of allocation that we just looked at. Or a trade-off between survival and fecundity. These are rotifers. This is a pregnant rotifer with its eggs. This is a rotifer feeding here. They move and feed usually with the feeding of these cilia. And they'll beat those cilia, and the water will flow into them, and they'll consume the things that they ingest, a whole manner of things, including just dissolved organic matter or plankton, zooplankton, phytoplankton. Those are rotifers, very common organisms in aquatic environments. Well, how fecund they are, their reproductive effort influences their likelihood of survival. The greater their reproductive effort, the less likely they are to survive that year or the following year. So there's a negative correlation between survival probability and fecundity in this study population of rotifers. Again, illustrating the model nicely. Look at it in terms of survival there. Again, survival and reproduction or fecundity. This time in a bird, European kestrels. We have a kestrel here in Berkeley that's very similar. A little bird that likes to eat small rodents, catching them in fields. Great bird that you can see on phone wires just over the hill if you go looking around on a warm day. This was an experimental study. A lot of the insights in ecology are based on actual manipulative work of populations and organisms. And in this case, what the investigators did was actually manipulate how big the brood was of these birds, how many chicks they had in their nests. They would actually take chicks from one nest and put them in other nests. So they would reduce the sizes of the broods for certain pairs of parents and increase the size of the broods for other pairs of parents and leave other pairs of parents untouched with their normal brood as control. And what they found was that the parents that raised larger numbers of chicks had a lower probability of surviving the following winter. Both parents, in a case like the kestrels, help to provision the young. So they're out there foraging, catching things, and bringing them back to the young. And the more mouths there are to feed, the more energetic investments required on the part of the parents to find food for the young. And that burning of energy and procuring food for themselves and their young influences their survival in the difficult season of the winter when food is in short supply. They've lost their energetic reserves that would allow them to maintain themselves in that winter. Now, you can look at the original study. The Campbell figures actually seems to be a little mixed up. They have their males and females reversed. They have the magnitude of these differences altered. I don't know how they did that, but it seems to be off of the original figure. But the point remains the same. I don't think they missed the point in mixing up the data. But this should be more or less accurate here now, the way I changed it. So these life history traits, and that's what we can call them, these various aspects of life history, various aspects of the organism's life that have to do, for example, with the timing of their reproduction, the age at which the organism first reproduces. A little vole, a little meadow mouse, might start breeding at 3 weeks of age. And that's obviously different from what a rhinoceros is going to experience. At 3 weeks, a rhinoceros is learning how to walk, not learning how to breathe. It's going to take some years. So the age at which the organism first reproduces varies species to species. It can even vary population to population. Many of these life history traits we don't think of as fixed for a species. They're labile. They can be responsive to environmental circumstances. The size of the clutch or the size of the brood, really just another name for brood, a clutch. Well, do you produce 3 eggs or do you produce 6? Organisms can vary that much in their brood production. And again, although the range of that size might be characteristic species to species, 3 to 6 eggs, 1,000 to 1,500 eggs. Those might be characteristic of different species, but within that there's a lot of variation in play that allows organisms to be also responsive to local environmental factors. How are the young born? Are they precocial or altricial? Well, that little meadow-mouse is born relatively precocial. Many animals that are born in environments where there are a lot of predators are born precocial because they need to be ready to, say, run or fly in order to survive. Others are more altricial and dependent on the parents for their early survival. So the degree of precociality or altriciality can vary. How many reproductive events are there during the life of the organism? Is there just one, or are there many? And if there are many, are there a few, or are there a lot? All these things vary. And all of them are important demographically in terms of how they influence population dynamics. In terms of this last one, the number of reproductive events during the life. An organism, and this is just one example, is a scorpion, which are actually really interesting creatures. And they carry their babies on their backs. In a case like this, the mother does. Well, she'll breed this season, produce all these little scorpion babies, and do it again the following year, or maybe even at another point in the same year. The point is, she reproduces repeatedly during her lifetime. She's iteroparous. Itero, just to repeat, right? Paris has to do with giving birth, so repeated births. Human beings are iteroparous because they reproduce repeatedly. Now, not all of us reproduce repeatedly, or at all. That's not what, so we don't speak of an individual being iteroparous or not. It's really a characteristic of the species in this case. In contrast, some organisms are semelparous, where they'll reproduce only once. And there are some great examples of this. For example, plants in extremely arid environments, like the century plant, may live for 100 years. In the case of the century plant, it can live 100 years. But when it's time to reproduce, it undergoes this big bang reproduction where it invests everything into that one reproductive event, and then the plant will typically die. What kind of environments? I mentioned the aridity of this area, but what kind of environments would you expect to give rise to creatures like this, evolutionarily? Semelparous? Yes. Something extreme, an extreme environment. Why? Yeah. An environment that has few resources? Yes. Yes, they do. Salmon do die after this one. That's a different case. Yeah. Oh, and it's my next slide. Yeah. Yeah. Too costly to reproduce every year, you mean? That can play a role. Too costly to reproduce every year because resources are in such short supply. Right. That's a nice point. Yeah. Yeah. Excellent way of thinking about it and setting it in the context of the principle of allocation, where in these difficult environments with few resources, you can't dedicate resources to reproduction year after year because so much needs to be dedicated to basic maintenance. Similar to the point that was previously made. Yes. There's also an unpredictability of a particular season in extreme environments like this. The environment does become suitable for reproduction in certain years, but that's often unpredictable, whether it's going to be 3 years or 10 years in the future. And yes, so the organism needs to hedge its bets about when it should reproduce, because if you pick the wrong season, you'll fail in your reproductive effort if resources are inadequate. So what organisms like this will often do is, when the rain hits, in a case like this arid environment, when the rain hits, then they go for it. They put it all into that reproductive effort. There are mammals that do this. There's a marsupial mouse in South America where the little males spend so much of their energy in territoriality trying to compete for females that when they finally breed, they die. The little male mouse does. And the female carries on and rears pups. Yeah, it's a pretty spectacular mammalian example. Not too many examples in the mammals. Salmon. Yes, we have, at least we used to in this part of the world, have these spectacular salmon runs. They still exist in some areas, but dams have, of course, taken a heavy toll on them. Salmon, as you may know, like this, are born in high up rivers. They're born there, and then as they grow, they move down the rivers into the ocean, and they may spend years in the ocean before it's breeding time, and they'll work their way back up the river, typically the very river where they were born, which they home into, and go back to their birthing ground and spawn there as adults and produce their young there. And the males and females migrate together. The males morph along the way into these very vicious creatures that the males compete with each other with these big jaws and big teeth. They actually morph along the way, breed at the headwaters or wherever their natal grounds are, and most of them die. They've put a ton of energy into that traveling event and all that battling between the males and all the dodging of grizzly bears and fishermen with pitchforks, because the great sport in some of the Pacific Northwest is just to go out there with pitchforks. It's empty and just hook them and throw them over your shoulder. You don't even have to fish for them. And you've seen the grizzly bears that fluff them, and they get so greedy and full on them that they just start eating the eggs out of the bellies of the females or eating the brains and leaving all the rest, which the gulls clean up. And it's a huge feast. The wolves come down. There are deer that might come down and eat a carcass of a salmon. It's a huge influx of resources from an ocean environment. Can go well into the continental environment. Neat connection between marine and continent. And this is a semelparity that's not related to a shortage of resources in a particular season, but related to the massive investment that's required to actually breed, much like what the little marsupial mouse experienced. And there's just nothing left for survival after the fact. A very small number of the salmon do survive this, but the percentages tend not to be high. Was anyone rooting for the bobcat? All right, or a few of you. Yeah, so in the case of these ground squirrels, and these are not an uncommon mammal up in the Sierras. You can go in the Sierras just a few hours drive and see these creatures. They survive the extremely cold winters up there by hibernating. They can lower, through hibernation, they can lower their body temperature below freezing. Basically, they can go into extreme hibernation and almost down to 0 degrees centigrade in body temperature. The females tend to stay around the native home, where the males are more likely to disperse for up to a couple of kilometers away. That close relationship among the females in an area is what can help explain those altruistic calls that are given as a warning of predators. You may have gotten some of that in evolution too. The likelihood of the altruism there increasing as a result of the close relatedness of the females in these groups. It's usually the females that actually make the calls. So what has been done up there in a series of studies is the following of Belding's ground squirrels as populations in terms of these life tables that demographers use to track population dynamics. This is usually not done for a whole population just because it's too difficult to track individuals across years. And in this case of this study, it's a 10-year study. You can't do that for the entire population, so you follow a cohort. You follow a group of individuals that you isolate. Ideally, individuals that are of the same age, that are born in the same year. That can be your cohort that you follow, and you just neglect everyone else. Often, in terms of the reproductive side of life history, you just follow the females. It's just because the females are the ones that bear the young. You can just follow the females and exclude the males entirely from the analysis, and that works well too. So then you can narrow your study further to make it viable, because this is really difficult work to do year after year. Now, these guys hibernate for that winter, so they're really seasonal creatures in their activities, right? And the reproductive efforts happen at these annual intervals. So it's a nice organism to study at fixed intervals in terms of their population dynamics. A survivorship table like this is built on, and these are formal columns that are used in a table like this, that then feed into the population ecology models that ecologists use to study the population. What are tracked are the number of individuals alive at the start of the year, or in the original cohort. In this case, 337 females were alive at the start of the study, age 0 to 1 year. So those are the ones that were born. They're all alive at the start of the year. The proportion alive is 100%. And what's tracked is how many died during that year. And what can be computed is a death rate, a per capita death rate. So if 207 female squirrels of that original 337 died in the first year for a death rate of about 61%. And that can be tracked year after year. And the death rate can be checked over time for the female squirrels, and also in the same way for the male squirrels separately. The reason these survivorship curves are often broken into females and males is because the females have a different dynamic from the males oftentimes. Look at them in this case in terms of survivorship. 61% of those females survived that first year. Sorry, 61% died, but fully 65% of the males died. Second year, 50% female, 56% male. 47% female, 69% of the males died. So you can see a great difference, and the oldest males to survive among that cohort were just 5 to 6 years, whereas there were females that carried on till age 10. So that's a very different dynamic, and leads, I think I'm going into survivorship curves, yeah, and that leads to a different shape to a survivorship curve, which is based on the data from a table like that. It's just the original cohort, and here standardized at 1,000 to make it easily viewable on a curve like this. If you start with 1,000 individuals, all you have to do to get these points is multiply out the death rates. And you can, in doing that, see how the male curve, the shape of it, the slope of it, is different from, the male curve is different from the female curve. It's more steeply declining, showing the fact that the males experience higher mortality rates over their lifetime and live for a shorter period. Now, this is on a logarithmic scale, right? So I trust you all remember the difference between a logarithmic and an arithmetic scale. Because as we saw, that death rate at 60%, some 60% in that first year would cause, some 600 of these individuals to die. So it's a pretty precipitous drop. But if you notice, these death rates, they're actually fairly constant, around 50% throughout the life of these squirrels. Throughout the life history of these populations. It's fairly even. The likelihood of dying at the cohort level is relatively similar across the years. There's always high mortality right around the birth. But after that, the likelihood of dying is relatively constant. That's what gives this a relatively linear, flat shape to the curve. It's called a type 2 curve in the survivorship curve context. And on a logarithmic scale, it's basically a line. If this were on an arithmetic scale, there would be a different shape to that. Here's an organism that produces a whole lot of offspring, and I'm not sure if these are sperm or eggs. I don't know if that's the female or male production there. But the point is, it's a huge number of gametes that are put out. Not all of which, the vast majority of which, won't survive the next couple of hours. The fish are going to start to swarm, the zooplankton are going to swarm, and most of this, and they're going to drift, and most of those things are going to die. They're not going to make it. There's a precipitous drop in numbers, a huge mortality rate in that very early phase, causing this steeply declining curve that eventually levels out. Because if you become a big clam on a reef, there's not much that's going to dislodge you from your life over the next many years. You get your space, you get big, you become almost invulnerable after a certain stage. That gives rise to this type of curve, type 3 curve, typical of many marine organisms, many trees. An oak tree is going to produce a huge number of acorns, a very few of which are going to actually survive to become big oaks. But once they become a big oak, they may survive for quite a long time and reproduce many, many times. Or there are our rhinos again, exhibiting a phenomenon where only one or a couple of young are born. They're big at birth, and they're well taken care of by the mom against the lions and hyenas. The mom protects the babies, and that investment of parental care increases the likelihood of survival on the part of the young. So the likelihood of survival at the early ages is actually relatively high. At some point, they reach their lifespan, and the group undergoes a precipitous decline in numbers. The population drops in numbers, and that's also typical for humans, right? Everyone starts dying around a certain age. That age keeps creeping up. Just 100 years ago, the average lifespan was much lower. That keeps climbing, but the shape of the curve remains more or less the same. Again, there's typically high mortality that's not often shown on these graphs in the perinatal period, including for Homo sapiens, even with the best hospitals.